Hi everybody. So let's take a little bit and talk about the electric field. So far we've talked about charge. It can be positive or negative. We've talked about how um, uh, uh, like charges repel, um, and opposites attract. Um, we've talked about how we can use Coulomb's law to describe the force between charges. So if you have a couple charges uh, separated by some distance, the force between them is this inverse square law. It depends on the product of the charges. So the bigger the charges, the bigger the force. It's inversely proportional to the distance, and it points along the line between them. So in this picture, that would be along that unit vector along the vector that connects them. So and this is similar, it's the same mathematical form as the force of gravity, except with gravity you can't have negative mass. So now it adds a level of complexity in terms of keeping track of things because we can have both positive and negative charges. And we looked at a couple problems where we had configurations of charges and we used Coulomb's law to find the force and the magnitude and the direction of the force. And we also mentioned, although we didn't emphasize, that we can generalize this a little bit by noting that you don't have to just do two charges. If you want to find the effect due to multiple charges, say on Q1 here, the net force is just the sum of the contributions from all of those charges. And this is a pretty powerful principle, actually. And this is called superposition. So in other words, this electric force obeys superposition, as does gravity. However, this, as you've been working problems and stuff, I suspect you may have noticed that this picture, this way of going about this, does have some limitations. So it's kind of cumbersome. You can imagine you wouldn't want to do more than a handful of charges here because you would end up with tons of components that you have to keep track of. So let me just call this limitations here. Limitations to this approach. It's not very general. So what I mean by that is, suppose you move this charge. So let's oh, come on, computer. If we move Q1 up here, you would have to redo your calculation, right? So it's not very general. And another thing is it doesn't handle things that aren't points. So it doesn't handle basically objects, things with size. I'll say extent, how about? So you can imagine, if you had imagine some metal thing that you've touched to something charged and charged up, so it has charge on it or whatever. That object is not captured in this picture because it's not a point. You can't just add up, the charge of some point because it has size. So as you can imagine, we're going to have to extend this picture. All of this motivates this idea of the electric field. So like often happens in physics, we add a layer of abstraction. So we use a little bit more sophisticated idea, the field, rather than just force. And this gives us a more powerful way of solving problems and approaching problems. So the electric field, what is that exactly? Well, the simple definition is just that the electric field is the electric force per unit charge. And it's you've encountered something like this before potentially in 2011. There's also so it's similar to the gravitational field, which you may have talked about in 2011. So in that case, that was the gravitational force per unit mass. And we use that to think about, to imagine sort of the acceleration due to gravity around, imagine like in outer space around a planet or something where it's not constant. You can sort of map out what gravity would look like. And for the problems that we did, it didn't really let us calculate anything because what we did in 2011, almost everything, we didn't work with any non-spherical planets. There weren't any square planets or anything. Everything was spherically symmetric. And as you know, if it's spherically symmetric, it looks like a point when you're far away from it. So it didn't really let us solve any kinds of problems. That's not to say there's really cool and exciting research happening with the gravitational field. And if you've Google LIGO sometime, this observatory that detects gravitational waves. So there's tons of really interesting stuff with that. But it didn't really let us solve problems for what we were up to in 2011. The electric field, though, that abstraction will. So you can think of this, so in the gravitational analogy, you imagine a test mass, like a tiny mass, a sensor, say, and you move it around and you would map out the gravitational field with it. The mass would be small enough to where it's not going to have any effect on the surroundings. It's kind of the same idea with the electric field. The conceptualization is you imagine moving a tiny charge around and mapping out the field. That charge doesn't have any effect, but it kind of lets you detect what's going on. And then what you do is, if you want to know the effect of that electric field that you've mapped out, the force is given by whatever charge you put there times the electric field. So if you used, actually I'll put a different letter Q just to distinguish between the test charge and the charge that you're interested in, the effect on the Q that you want to examine. So let me give you some examples. So there's one example that you kind of already know the answer to, and that is the point charge. So if you have point charge, let's say, let's just call it Q1. If it's positive, there would be, the electric field would point away from it. And when we calculated, so we'll just apply our definition here. The electric field is going to be the electric force per unit charge. So the electric force due to a point charge, is KQ Q over R squared. So if you then divide by that test charge, sort of cancel out one of your Q's, and the electric field due to a point charge looks almost the same as our expression for force, except it's KQ over R squared. So we've lost a factor of charge. And the real and important takeaway from this is the functional dependence of this. So this looks like 1 over R squared. So this is E field due to a point And you can imagine mapping that out everywhere in space. So think of like, kind of how I'm thinking about it is like you could see what that looks like everywhere. This field that kind of permeates a volume. Now, the powerful thing, or a powerful thing with this, is that we can use superposition just like we would with the force. So the electric field also obeys the same principle. So if you had another charge, you can do the same thing. Suppose, Q2 is negative here. So you could add up the electric field contributions from as many charges as you want, or as you have, and calculate the net electric field. And then if you want to know how what force a charge placed in that field is going to experience, it would just be, whatever charge you put in times that net electric field. Now, where this gets interesting is when we start thinking about objects. So things that have size. So we'll work through an example or two. So in this case, instead of, this, you could think of this as being a sum of discrete let me write it like this. So this is the same thing as like a summation, where you add up over all the electric field contributions. If you start talking about an object that has size, as you can probably imagine, this sum becomes an integral. And what it amounts to is we need to break up our object into pieces into something that we can integrate. And a really good example for this. So it turns out a really an excellent system to look at to explore this idea of an object is a really simple object, and that is a wire. So imagine a wire, and we're just going to center our coordinate system on the wire. And we want to know what's happening to the electric field at some point above it. So in this case, since the charge distribution is one-dimensional, instead of Q, we're going to work with something that's, by convention, we use lambda. And this has units of coulombs per meter. And the idea with this is so this is the charge density per unit length. If you multiply this by some length, that would tell you how much charge you have. So why we need this is because we're going to multiply this by some differential length, and that would tell us the differential amount of charge. So kind of the cartoon, imagine a little snippet of this wire, which we'll identify as dx. We're going to need to know the distance, call that r. Call this y, this x. So that kind of gives us a picture of the geometry. We're also going to need to make use of this angle here. Okay, so one thing that's important to recognize from the get-go, because it will help us simplify this problem, is symmetry. So if we're considering just a contribution from the right side of the wire here, suppose the wire was positively charged, you would imagine the electric field contribution from that little snippet would be pointing like that. Now recognize there's going to be a location over here that would have the same effect, but is going to be pointing like that. So notice both of these would be pointing in the y direction. They would both be pointing up. But in x, this one is pointing like this. This one is pointing like this. So those contributions would cancel. So, and I'm going to remove this just to keep our diagram a little more tidy. But what this is telling us is that the EX contributions are going to be 0 because of symmetry. And what this also means is that, if you think about it, the total electric field is only going to be pointing in the y direction. And so we'll make use of that when we go to integrate. So what we also need, we want our differential electric field contribution. So it's going to look just like Coulomb's law. 4 pi epsilon naught. We need our dq over r squared. Now, we can substitute in this piece of information. So this will become 1 over 4 pi epsilon naught lambda. And actually, let's put it in terms of x, because that's what we're going to be integrating over, dx. And we can also recognize that this r squared, we could write that as x squared plus y squared. Just think about Pythagorean theorem there. So now, like I mentioned up here, the total that we're concerned with, to get it, we're going to integrate this, but we're only going to be concerned with the y contributions. So if you look at our picture, we're going to pick up a factor of cosine in here. So in other words, maybe net. I think I'd been using the terminology net before. It's going to be EY, and it's going to be, so this differential and we'll pick up a factor of cosine. Now, you can see pretty quickly that there's a mathematical challenge with this because we have an integral over x, but it contains an angle. So you can deal with this in different ways. One way is we could put everything, we could put that angle in terms of x and y. And let's try that first. So one thing that we could do is note that cosine theta is the same thing as y over r. So same thing as y over r, and r is x squared plus y squared square root. So then we could substitute this in, and we would find our integral would, so I'm going to pull out the constants and stuff. Reorganize this a little bit. We would have y dx. We would have this x squared plus y squared to the 3 halves if we combine those two pieces. So we've just substituted in the cosine. And we could simplify this a little bit further. Notice we're integrating over x, so we could pull the y out as well. But this integral is not obvious. I'm actually curious if you've encountered this before in calculus. So question for the comments on this video. Have you seen this before? You messed with integrals like this? I'm just interested. So put it down in the comments. So if you run into an integral like this, there's different ways you can solve it. You can plug it into a computer. You can look it up in a table. Back in my day, we would crack a book that had big tables of integrals like this. One thing that we can do to make this simpler, this is the general expression when we're really integrating from negative x to positive x. But let's make the wire really long. And so we'll integrate from negative infinity to infinity. And you may find, or you may have learned this kind of already, sometimes these integrals that look kind of complicated, when they're definite integrals, when you apply your limits, you actually end up with a pretty concise result. And that's what we see in this case. So when you integrate this, you would find that this thing is 2 over y squared. So we get lambda over y 4 pi epsilon naught times 2 over y squared. So you could, if you have Mathematica or something, you could evaluate that. Notice we'll lose a factor of y. So we'll simplify slightly. And we find that the electric field is going to be lambda over 2 pi epsilon naught. And that's one way of going about this. And we can connect this to the way that it's done in your book. So another method, just to sort of flesh this out a little bit for you, so you can connect it to what you're reading. So the way they go about this in your book, they make a substitution. So it's really a substitution. Instead of working in x, y, we're going to work in theta. And they base that off the fact that if you connect x and y to theta through tangent theta, you know that x is y tangent theta. And you can recast dx. So this would become 0 times derivative of tangent plus y times derivative of tangent with respect to theta, which is 1 over cosine squared, times derivative of tangent, or theta. So we can substitute for dx. We can also make use of the fact that cosine theta my picture's a little off the screen. So cosine theta is going to be y over r. And so we can also, we could square that and note that cosine squared theta is y squared over r squared. And so we can substitute that in. Remember, r squared is x squared plus y squared, so we can substitute the denominator of our integral to put it in terms of cosine squared. And do we need another ingredient? I think that is everything that we need. So let's substitute these pieces in. This will become, well, actually here, let me pull out the constants. Lambda over 4 pi epsilon naught. So the 1 over x squared plus y squared would become cosine squared over y squared. Okay. And then we have this additional factor of cosine theta due to the y component being the only contribution. And then we would also have our dx, y over cosine squared theta d theta. And notice most all of this stuff is going to cancel out. So we lose those terms, lose that, and we end up with lambda over 4 pi epsilon naught cosine theta, one factor of 1 over y that we can pull out. And cosine, so what we've done is we've traded sort of a complication with changing what we're integrating over, and it makes the integral way easier to evaluate, right? Because you know how to integrate this. So this is just sine. So, and I should say, if we employ the same limits, so if we're talking about a really long wire, what that corresponds to an angle would be from negative pi over 2 to pi over 2. And all that we get from this is we pick up a factor of 2. So this would become, this stuff times, because sine of pi over 2 would give you 1 minus negative 1. And we would end up with the same thing as we should. Times 2, so this would cancel, and we get the same result. Now, I just showed you these two methods because the thing that I want to show you next is going to use kind of what's on the left. So the thing I really want to draw your attention to with this is the functional dependence. So notice in this case for the wire, the electric field goes like 1 over r, not the point charge was like 1 over r squared, just like Coulomb's law. So it has a different behavior based on the geometry, which is kind of interesting. And let's extend this. So rather than a wire, what could we look at? So we extended it from a point, which is 1-dimensional, to 2 dimensions. Let's to a 1-dimensional wire. Let's extend that wire into a plane. So imagine now. Actually, let me give myself some more room here. Now, instead of a wire, imagine a plane. Kind of the same situation. So, imagine your coordinate system x and y, and we want to know what the electric field is doing above this plane. So this will be z. Instead of a little linear charge contribution, imagine a little chunk of area. So this distance will be r. Each chunk of this, this would be x. This would be y. And again, we're going to be concerned with the angle. We'll call that theta. let me move this. So this is the y-axis. X. Oh, I drew these backwards. Sorry. Okay, so now it's exactly the same kind of situation. You can imagine electric field contribution from this little patch would be pointing in this direction, but you could just as easily find a little patch that's mirrored through the origin, and it would be pointed that way. And you could see how these horizontal contributions are going to cancel out again. So we are only we're only caring about the part that's in y, or sorry, in z. So ex, ey are both going to be 0. And what this means is that the net electric field is going to be just the contribution from z. So we need our little differential electric field contribution. It's the same sort of setup. Oh, I forgot one piece of information. So instead of multiplying lambda times the length, in this case, we would need a little differential area, and the area charge density is usually called sigma. So what this would mean is that if you have, some patch of area times sigma, that would tell you the total Q on that piece of area. And so this would have units, of course, of coulombs per meter squared. And in x and y, this differential area becomes dx times dy. Okay, so we need to take our, so what are we going to integrate? We're going to have 1 over 4 pi epsilon naught dq. So our dq is going to become dx dy sigma. And then this will be, again, just like Coulomb's law, 1 over r squared. And it's the same situation. So we're going to pick up a factor of cosine theta. So let me, now our integral becomes a little bit more complicated because we need to integrate over, let me move this. We need to integrate over both x and y. It's just going to be the z contribution. So as a question for you, actually, have you encountered multiple integrations like this, multiple dimensions? So you can let me know in the comments if you've seen something like that before. I'm curious. So let's write this out. We would have sigma 4 pi epsilon naught, our cosine theta. Now this brings up, what is r going to be? Well, when we had this before, it would just be x squared plus y squared square root. Now in this case, since we have another dimension, r, you can see this would be the x piece squared plus the y piece squared plus the z piece squared. Okay. So we're going to make use of that piece of information. And then we can also rewrite our cosine in terms of this. So actually, let me pull out the constants. So this would become cosine theta would just be z over r. And you can see we also have a factor of r squared. So this would again be, our denominator would be power 3/2. So this integral is more complicated, but it's the same kind of, it looks really similar to the first way of looking at the wire. So if you evaluate one limit or the other, if you evaluate over x or y. So again, we're going to use the case where we're imagining this plane gets really big. So our limits of integration would be infinite. What you would find is, and you can check this, try evaluating this integral on a computer or something. So the integral doesn't depend on z, so we can pull out that factor of z. If you integrate over one dimension, you would get, what do you get? You get a factor of 2. So when you integrate over one dimension, you get 2. And what you're left with is, so let's say I integrated over y or x. And so I'm left with the y integration. This reduces to y squared plus z squared. And then when you integrate this again, when you do the y integration, find that this integral gives you just pi over z. And we can simplify this. Notice almost everything here cancels. Pi cancels, z cancels, we'll lose a factor of 2. We're left with sigma over 2 epsilon naught. And notice, so this is E for a plane. And this would be solely in the z direction as we have it written. Or if we were using our unit vectors, this would be k hat. Notice we were talking about functional dependence with the point charge and the wire. This doesn't depend on how far away you are at all. So this is pretty neat. It does not depend on z or r or whatever you want to call it. So in other words, this is constant. So if you have, just to draw a picture, these field lines are not spreading out at all. If you it's just interesting that this charge configuration has a lot different behavior than the other ones that we looked at. So the wire goes like 1 over r, and the point charge goes like 1 over r squared. So hopefully this gives you a flavor for kind of the connections between what you've probably seen in calculus in terms of some more complicated integrals, and where those sorts of integrals appear. So they can show up in these Coulomb's law problems when you're talking about objects that have size rather than just the ideal, just points. And don't worry about I'm not going to throw some curveball integral at you. There's actually a much more powerful way to derive these sorts of expressions that we'll look at in the next chapter. So